And then for next week, we'll start Chapter 2. And as I mentioned, I'll post to Homework 1 ASAP. Likely, I will post it tomorrow, Saturday. And maybe we'll have it due a week from. There's also the, as you probably know from last quarter and your other classes this quarter, so what is it called? The confirmation of commencement of academic activity, right? Remember that? Okay, so the TA will set up a quiz within Canvas that's linked to, I don't know, # financial aid or something. So that if you take the quiz, then the information, the data will automatically go there to wherever, so that it'll confirm that you have commenced your academic activity in this class. Now, the quiz will be, I don't know, one question, something like, what application of fluid mechanics are you interested in? Something just, very simple, just so that we can get that data sent, and especially for anybody who is receiving financial aid, apparently it's critical. Okay? So please, everybody, do that, and I'll post an announcement when that's set up. Okay? All right, and then I'm going to try to use these notes that I posted so that I'm consistent. We'll see how it goes. So there's that, and then there's this the quiz. It'll be like what we did in MAE 11. There was a quiz in Canvas that was linked, but in MAE 11 the quiz was technical, but here it'll just be some simple question. All right. So in terms of the stresses, I just want to make. I wanted to make a comment on this. So recall that I was discussing the fact that when you have some object moving in stationary fluid, or if we fix the coordinate to the object, it's an object that is that has fluid moving around. And as I mentioned, whenever there's relative motion between fluid and some surface or an object, then there will be a resultant force, right? So I had in this in the notes some sketch of what is referred to as an airfoil, which we saw a little video of, and it could be like a cross-section of a wing. And so if I sort of indicate the direction of the flow, I might do something like this. We'll go over, I think it's in Chapter 3, how fluid motion is represented. This could be something referred to as streamlines, which are lines everywhere tangent to the velocity, so they do indicate the direction of the flow. But in any case, the point I want to make is that based on relative motion and the behavior of the flow, then there will be a net resultant force on the object. Okay? And as I mentioned, that may be the objective of the analysis. We could break it down and have the component in the direction of the flow, which would be the drag force, and then the component perpendicular, the lift force, etc. Now, we're interested in forces, but if you more generally, it can be described in terms of a stress, which is force per area equals stress. Okay? So in general, there will be stresses. Anywhere in the fluid, there will be stresses, force per unit area, within the fluid due to interaction of the fluid surrounding fluid. And so I'm going to discuss this more in detail here, but what I wanted to point out is, so I had discussed last time that based on the motion of the fluid, there may be a pressure distribution, okay? Pressure varying within the fluid a certain way. And to get the contribution of pressure, which has units of force per unit area, right? Pressure, Newton per meter squared, or Pascal. So the pressure will contribute to this force. And so one would then, in order to determine that contribution, look at the pressure at the interface between the fluid and the solid. And then there would be a pressure distribution along that surface, that area. And so you would take the pressure acting over the entire surface area of this object, the pressure, which is force per unit area, and then integrate it over the entire area, okay? And as I will explain very in detail, pressure is a normal force, contributes to a normal force. So we'll always, this pressure, force per unit area, will result in, locally, if I look at this, say this differential area, the corresponding force will be a force acting towards the surface. Okay, so I'm going to go over the details of this here. Okay, so pressure will contribute to, and act as a normal force across an area, but then there is this relative motion, and the fluid is moving past this object, and we discussed it last time, that would result in a shearing or a tangential force. Okay? And that is associated, that can be thought of as friction, but it is associated with viscosity. It's a viscous force. Okay? But more generally, we consider it as a viscous stress, force per unit area. So along with pressure contributing to as a force, and pressure will result in a normal force, there will be a tangential force also along the surface. Okay? And that tangential or shear force will also be, if you know what it is, the distribution, can be integrated over the entire area and get the associated shear force and contribution to the net resultant force. So this net resultant force, as we will actually learn in 101B, this is more sort of in the advanced 101B, the details of this net resultant force, or essentially the drag and lift, will have contributions from the pressure, which acts normal to the surface, and then a viscous shear force, which acts tangential. Okay? So ultimately, what I'm saying is, ultimately, we're going to be dealing with stresses, and they can be very important for the practical objective of, for example, determining the net resultant force on an object or surface. Okay? And in general, there would be normal stresses associated with pressure, and shear stresses associated with viscous effects. Okay? So it's important to really understand this. Now, shear, this viscous shear force is associated with relative motion. When you don't have relative motion, or if you don't have motion at all, for example, fluid at rest, which is what's in this, basically what's here in this room, right? Then all you're left with is pressure. So that would be the stress occurring in the fluid. Okay? And that's where we're going to start off in Chapter 2 looking at. But in general, once the fluid starts in motion, we have to consider both. So I'll talk a little bit more. What is that? Okay. So we're going to talk a little bit more about this in Chapter 1. Okay? And then I'm going to repeat all of this when the time comes. Because I find some people, it takes a little while. So I may repeat it. in Chapter 1. I'll repeat it again in Chapter 2 and Chapter 6. Okay? All right. So let's go back to the basics. What is a fluid? And it's actually sort of relating to this. So I don't know how far. You guys can still see if I write on this board? Okay. So, and you have the notes, which I'm going to try to follow here. Exactly. So what is a fluid? So as I mentioned last time, okay, it's some substance that flows. We could consider the phases of matter, and there's the solid phase, and then there's the liquid and the gas or vapor. Okay? But in general, we combine these, and these are both considered fluids, right? So from the point of view of mechanics, there are solids, there are fluids. Okay? So there's that. Now, we could look at the molecular structure and distinguish these. Certainly, we know that, so if we compare solid, liquid, well, a solid, if I had a cube of steel, I could just carry it around, set it on the table. It retains its shape. A liquid, I can't just carry it around, put it on the table. I need a container. So let's put this like maybe a beaker. It could be an open container, a beaker, a cup, a glass. And there would be a free surface that forms, and a symbol denoting a free surface is this upside-down triangle. Okay? And then there's gas. And gases, we know, I mean, they have to be contained. So if I had an open cup, the gas may just, leave. So a closed container, and the gas is a fluid or a substance that would fill out the container, right? Whereas the liquid would maintain its volume in a container. So if I consider, where's that? Way over here. So we could look in terms or describe the behavior and explain the behavior in terms of the molecular started off too low. Molecular spacing. Okay, so solids, they're closely packed, the molecules, so small. And this would be moderate. Whereas the gases, I mean, these are molecules that are moving all over the place, and so they can be very large. We can consider the intermolecular forces. Solids, of course, the intermolecular forces are very strong. Whereas now liquids, this is smaller or moderate. And then gases are very low and, in fact, neglected in ideal gas. And then we have, and I'm sorry, now poor planning, huh? Maybe I'll write, since there's this thing, I will write the next row of information above. And so the third, we can look at the volume or shape, which we sort of already discussed. So the volume of shape, so the solid maintains its shape, the liquid maintains the volume or the shape of the container. It may have a free surface, and then the volume can change. There's just no definite volume, so it would just fill out a volume in a container. Okay, so we can describe the various phases in that way. But now, for the purpose of our analysis and to be more rigorous, the definition of a fluid, or the distinction between fluids and solids, is their response to an applied shear. So what is a fluid? The definition is a substance that deforms continuously under the application of a shear or tangential stress. Okay, so let's just consider a solid first. So let's say we have some block of a solid, and it is attached to a lower surface that is fixed and attached to some upper, maybe it's a plate. And on this plate, we impose a force, okay, which will then result in a shear stress on the solid. And so we can consider this shear stress as tau equal force per this area that the force is acting over. So maybe this is a cube, and this would be that square area. Okay, and so once I impose this force, then due to this shear stress, there will be a deformation. So let's say we consider this vertical line, and that vertical is going to maybe end up here, okay? And the solid will deform to some extent, okay? And this deformation we might consider as this angle here, this angle theta, okay? But at some point, it will reach some equilibrium because this imposed shear stress will cause internal stresses within the solid, and those stresses at some point will then end up being equal and opposite with its force, and there will be this equilibrium, and that's it. Okay? So at some point in time, that will be the total deformation that occurs. There's a balance of force, and we're in equilibrium. That's a solid. Whereas a liquid or a fluid, so let's consider the same thing. So we have fluid between two surfaces. So we have some fixed lower surface. The velocity is 0. And then this upper plate. And then we have fluid in between. Okay? And you know, we're going to do the same thing. So we'll impose a force on the plate. And so if we have some tank with fluid, like water, okay, and I just even put my hand on the top surface and move it along so that I impose a force per area or a shear stress on the fluid, we know that the fluid is going to move. So if we, for example, we could see what happens by maybe coloring a vertical line, putting a dye here, and there would be a vertical line in the fluid at the initial time, and then some small increment of time later, okay, that vertical line may have be something like this. Now, remember, there is this so-called no-slip boundary condition that occurs in fluid, no-slip boundary condition. So if the fluid has at the bottom, is existing over this lower surface, which I said is fixed. In both cases, it was fixed. And so U equals 0. That fluid, that piece of fluid, let's just consider some small fluid particle, okay, that is adjacent to the wall. And so that guy is going to be, maybe I can consider a cubicle, small infinitesimal cubicle fluid particle. And so because of this stickiness of viscosity, it's going to stick to the lower surface, okay? And so this fluid particle, infinitesimal, is stuck to the wall, so we'll take on the velocity of the wall, which is 0, okay? Meanwhile, for example, my hand, to apply a shear or tangential force on the fluid, okay, I'm going to move my hand along, okay? So associated with this force, the upper plate will have some velocity. Let's call it big U. Okay, so the velocity here is going to be big U. Okay? And the fluid particle at the top, which is just adjacent to the top surface, will be stuck to this plate, and so we'll take on the velocity of the plate. So this top fluid particle will have a velocity big U. Okay? And the fluid then is going to, there's going to be a variation of fluid. I mean, there will be some initial transient, but once this thing gets going and this force is maintained in time, and this is going to be then a constant velocity, then we're going to have this, we would see that the velocity of the fluid between these two fluid particles will vary. And for this particular problem, it happens that that variation is linear. So what was a vertical line within the fluid, those fluid particles along that vertical line would be displaced in this manner, and so there'd be deformation of the fluid, maybe similar to this solid, okay? So there would be like a delta theta within some increment of time, delta t. But it's continuous. As long as I keep moving the top plate, it's constant in time, but it keeps moving, okay? The fluid is going to keep moving. So at some increment of time later, okay, this vertical line would end up maybe being here. Okay, and then just time later, it'll be here. So there is this deforms continuously. That is, the fluid cannot resist a tangential force or stress, okay? Whereas a solid can. So the solid will deform a certain amount due to the imposed shear stress, okay? And as it turns out, for common solids, the shear stress is going to be proportional to the deformation. But here, there is a continuous deformation. So in this case, where there is this shear stress, which is this tangential force per unit area, we can't consider the shear stress to be proportional to a deformation because the deformation just keeps growing. And this is constant. So it is proportional to the rate of deformation. A solid cares about how much it deforms. And this shear stress is proportional to the deformation. A fluid will care about how fast the deformation occurs. So here, the shear stress is proportional to the rate of deformation, d theta dt. This d theta dt, you can consider it as this some increment of, what did I write? Q. This incremental deformation that occurs over some small infinitesimal time, and then one takes the limit as delta t goes to 0, and then we would get d theta dt, the rate of deformation. Okay? Now, we'll sort of return to this in a little bit. I considered the no-slip boundary condition. Okay. So the next sort of basic idea So we'll kind of come back to this. But the next basic idea is that of a continuum. So we kind of discussed this in thermodynamics. So if you're taking MAE 11 now, you might have already discussed it. But just that, of course, all matter and fluids consist of molecules. We sort of described that, discrete particles. But for most applications, we're going to consider the flow domain much larger than the spacing between the molecules, or the mean molecular path, or the mean free path. So in general, we're going to always assume that the fluid is continuous and consider a macroscopic perspective versus considering the motion and behavior of all the molecules. But ultimately, or physically, in reality, what the fluid does is due to all of the molecules that are, within the fluid. So from time to time, we may go back to a molecular point of view to understand why the fluid behaves that way, but all our analysis, we're going to assume a continuum. And that's pretty much applicable for most situations. But there are some that the assumption of continuum breaks down. For example, high altitude, the mean free path may be the order of meters. Okay, so now you may need to consider that and analyze things a different way. Okay, so we're going to consider continuum. Fluid consists of continuous matter. So the main implication is that properties such as pressure, density, and even velocity are continuous, very continuously. And they, for example, we can write this as the pressure is some function of, and in general, and in using Cartesian coordinates, the pressure is going to vary in 3D space smoothly. In general, also, it can vary as a function of time. And then the density as well. And the velocity, also a function of 3D space and time. Continuous variation. And so we can use differential calculus to describe this variation. And these properties, okay, can be evaluated at any point in space. Okay? So, if we have in 2D, so any point in space, we can define the pressure at that point, the density at that point, the velocity at that point. Okay? All right. All right, so let's just consider these variables in a little more detail. And some of this we did in MAE 11, but just to be sort of complete. All right, so density, denoted by rho, is, as most of you know, mass per unit volume. And how it is defined at a point. So we consider maybe the 2D space, okay, and we have this point, let's call it point C, and we consider some volume. Well, let's say it's in 3D. So some volume surrounding point C. And this volume, this incremental volume, delta V, and the mass associated with this volume would be delta M. Okay? Then we can define the density at point C as we take delta M divide by delta V, and then we take the limit as delta V goes to delta V prime. We don't shrink it down to 0, but we're now considering the fact that the fluid consists of molecules. Okay? So we're going to shrink this down to a very small volume, delta V prime. Okay? Small enough so that it's essentially a point when we're talking, macroscopic point of view, but large enough so that, if we have these molecules, gas molecules, for example, moving around, and then some may be just at that instant moving out of that volume. And so if we plot the density over versus delta V, if delta V is too small, then we're going to have inconsistent values of the density, because it would just depend. There's just so few molecules, right? So it would just depend on how many molecules within that volume at that time. But at some point, if we consider delta V prime, these fluctuations die out, and we essentially get a consistent density within, surrounding delta V prime, so that, the value of the density at that point is accurate. Okay, so that's what we mean by delta V prime, and once we go too large, of course, then we may pick up the actual variation of density that may be occurring. For example, in the air in this room, because since we're warmer, higher temperature than the ambient, we're locally heating up the air near our body, and it's changing, and it may have a different density. Okay, density, has units of mass per volume. So in SI units, kilogram per meter cubed. In English or British units, it may be slugs, that old thing that we all love, slug per feet cubed, or in English units, pound mass per feet cubed. So again, as I mentioned last time, you've got to be able to use the various units. Okay, so that's, in thermo, density of liquids versus gases. So if we're talking about properties of the fluid, okay, density is a thermodynamic property, depends on the state, so therefore may depend on temperature, pressure. But if you have a liquid, of course, we discussed this in thermo, liquids are hard to compress versus gases that are very compressible, okay? And so it's hard to change the volume for some quantity of mass of liquid versus we could easily change the volume of gas. So remember in thermo, recall, we had for liquids, we could assume they were incompressible substance, and the specific volume, which is inverse density, is essentially constant. Right? So for the most part, that's the case. And there is a plot in the figure, in your textbook, and I just included it in the notes. You can just kind of take a look at density as a function of temperature, and going from, 100 to 96 over a temperature difference of 100 degrees C. So we may have something like this. But there's not much of a variation in the value. This is kilograms per meter cubed. Not much variation of the density with temperature. So, it's essentially constant. But there are tables in the textbook, Appendix B. Okay, so physical properties of water. So there's temperature and density for probably 1 atmosphere pressure. So you can look up for a particular temperature the density of common liquids, right? Gases are highly compressible. and are dependent on temperature and pressure. So rho is some function of P and T. But for the most part, we can assume ideal gas. And there is the ideal gas equation of state that relates the density to the pressure and temperature. So I'm going to assume that you are all familiar with that from physics class or MAE 11. So recall pressure is equal to density times R, the gas constant, times T, the absolute temperature. Absolute pressure, density, the gas constant, which is equal to the universal gas constant divided by the molecular weight or molar mass. And then this has to be absolute temperature. Okay? So to evaluate the density for a gas, if you're given the temperature and pressure, you can use this. But there's also some tables. So in the notes, I included table B.4, which has density as a function of temperature. So this is for air at atmospheric pressure, P atmospheric. Okay, so at this pressure, it tabulates temperature and density. Okay, and so this would be kilogram per meter cubed. Okay, and then there is also this related quantity, gamma. So gamma is something referred to as specific weight. Okay, so the density is mass per unit volume. Okay, so it's almost like a specific mass per unit volume. And whereas if you have a solid, you characterize the mass of the solid object with mass. But for a moving fluid in particular, okay, there's not this fixed quantity of mass. So it's more appropriate to characterize mass with density, mass per unit volume. Okay? But as you'll see, especially when we start considering fluid statics, chapter 2, it is sometimes important to consider specific weight. So if you take density and multiply by gravitational acceleration, mg, okay, mg then is a force or weight, right? So this was mass per unit volume, but if you multiply by g, then you have weight per unit volume. And that's the specific weight. Okay? So this is gamma. And it's just convenient to deal with specific weight a lot of times, especially when you do fluid statics. So this third column is the specific weight, which would have units of weight per unit volume, so Newton per meter cubed. Okay, so get familiar with specific weight. Okay, let's move on to pressure. So we've got density. Now, pressure. So there is the consideration of pressure when we have a continuum. And so first, considering pressure and how it's defined at a point. So pressure denoted by P. Oh, by the way, I did want to, where is that? I did indicate density as mass per unit volume. And just a note, so if you've taken MAE 11 from me, you know that volume, which has units of length cubed or meter cubed, I denote using a capital V with a horizontal line, right? And that's to distinguish it from the speed, okay? There's the velocity, which in general is a vector, right? But we might just use V as the magnitude of the velocity, and that's a capital V, okay? And then also in MAE 11, where did I write that? Here, the specific volume, which is denoted by so this is volume per unit mass, inverse density, which is denoted by lowercase v in thermo, right? Sometimes, people write lowercase v like this. And so that's not good either, because how to distinguish between this and this? So this lowercase v, okay, the problem in fluid mechanics is that the lowercase v in general is used for the y component of velocity. So if we have x, y, z, three-dimensional space with, as described using Cartesian coordinates, and we have the velocity vector, okay, and that's the velocity at a particular point, we can break this velocity vector into the components in each of the three directions. And using the unit vectors, I in the x direction, j in the y direction, k in the z direction, then the x component of velocity in the I, y component, so there's the v, the lowercase v, j, and the z component of velocity in the z direction. Okay, so we have to be a little careful when we use specific volume, because in fluid dynamics, lowercase v is reserved for the y component of velocity. Okay. However, in general, in fluid mechanics, we basically deal with density, not specific volume. But we do deal with volume, total volume. So perhaps maybe you can, everybody can use this as total volume to distinguish from speed. Okay? Everything has to be very clear and precise, right? Okay. Pressure. So first, let's consider pressure in a fluid at rest. So maybe we have some, container of liquid or some fluid. And so here's point C. And so again, we consider some infinitesimal quantity. But now, since pressure is force per unit area, we can consider some incremental area surrounding point C. Okay? And so this area is going to be delta A. And so if we just look at this delta A, which could have any sort of orientation within the 3D space. So this is delta A, and here's point C. Okay, so if this is fluid at rest, okay, and let's say this area is oriented in this way, due to the fluid on the above this area, okay, there's going to be a force, a normal force, acting towards this area due to the action of the fluid above. It's a normal force, delta Fn. But this fluid is at rest, so there has to be an equal and opposite force associated with the action of the fluid below, on the other side of this surface. And so there's this delta Fn. So due to this fluid above, there's a normal force, delta Fn. But due to the fluid below, there will be an equal and opposite normal force acting on that area, delta Fn. Okay? And this is associated with the fluid above and below. Okay? And so now we can define the pressure at this point as P is equal to the limit as delta A goes to this delta A prime of this normal force over the incremental area, delta A. Okay? So we shrink this area down to a small enough area so that it's essentially a point. But again, large enough so that it's like that discussion of the density. It has sufficient molecules so that it's a robust measure of the pressure at that location. And the pressure, we know, is a scalar, right? So we consider it, it doesn't have any direction associated with it. It's isotropic. But the associated force, it does create a force, and the force has a specific orientation. But that orientation is always towards that area. And we can change the orientation of this area, but the pressure, it's just a scalar acting over that area, but the resulting force will always be acting towards that surface. And so the pressure is a compressive stress. It results in a compressive or normal stress. Okay, I think let's stop here because it's 10 of, right? Sorry, a couple minutes over. My watch is. And then we have, an hour? And then at 2 o'clock, I'll resume. Okay? And we'll really start talking more about the stresses in the next hour.